Look at this generated visualization of a standard computer vision task. At high resolution, every single pixel requires connecting to every other pixel simultaneously. Standard vision transformers fail under this load. They compute relationships using global self-attention, meaning the computational cost scales quadratically relative to the image size, what computer scientists define as big O of n squared. Feed a modern high-definition input into that architecture, and that quadratic scaling will instantly exhaust your GPU's available VRAM. To solve this, we must constrain self-attention to isolated local patches of pixels, which the architecture defines as windows. Isolating data into these fixed windows saves memory, but it breaks the transformer's ability to see the complete picture. Restoring that spatial awareness requires a highly specialized mathematical workaround. That workaround is executed by alternating two distinct mechanisms: window multi-head self-attention, or WMSA, and shifted window multi-head self-attention, or SWMSA. This technical document displays the exact 9-step sequence that defines the WMSA block, and this list shows the 8-step sequence that defines the complementary SWMSA block. Reading the high-level concepts from a list is insufficient. To understand how these blocks operate, we have to track the exact tensor-shaped transformations occurring underneath in PyTorch or CUDA. The efficiency of this architecture relies entirely on how it aggressively reshapes memory, tricking standard attention functions into processing localized data in parallel. We begin WMSA pipeline with a batched spatial feature map. This 3D block represents our initial tensor, formatted with batch, height, width, and channel dimensions. Step 1 is patch partition. The continuous spatial dimensions are discretized into a rigid grid of m by m patches. The tensor separates grid and window coordinates, expanding into 6 dimensions: b, h over m, w over m, m, and c. Step 2, window partition, is the critical operation. The batch, grid height, and grid width dimensions are flattened together into a massive megabatch. This produces the effective 3-dimensional sequence shape fed into attention: b times hw over m squared, and c. The sequence length, the middle dimension of our tensor, is now strictly capped at m squared, which typically locks the size to 49 or 64. By moving the image's spatial scale out of the sequence length and into the batch dimension, the hardware calculates localized attention in parallel with strict linear complexity, O of n. This grid represents steps 3 and 4. Query and key projections execute on the tensor, forming an m squared by m squared attention matrix. In step 5, a pre-computed scalar bias tensor is added to the logits, retaining spatial awareness within the isolated window. Step 6, softmax, and step 7, multiplying by the values, execute identically to a standard transformer. Moving to step 8, window merge, the tensor must be reassembled from the isolated sequence format back into a continuous spatial block. The output shape reverts precisely to our original 4 dimensions: b, h, w, and c. Step 9, projection back, finalizes the block by passing the data through a linear layer. WMSA isolates the windows perfectly. However, it leaves us with a fractured view of the image. Connecting the context between those isolated grids mandates the SWMSA block. We transition to the SWMSA block, which is engineered to allow data to communicate across the rigid window boundaries we just established. The process hinges on step 1, cyclic shift, which replaces computationally expensive padding. This top-down grid shows the torch.roll operation. It shifts the tensor up and left by half a window size. This creates a direct hazard. Pixels from opposite corners of the image are now physically grouped inside the same local window in memory. Step 2, window partition, blindly processes these newly formed mismatched windows as if they were a continuous space. If standard attention runs on this shifted tensor, the model will learn false spatial relationships between the extreme edges of the image, entirely destroying its accuracy. Step 3, masked QKV attention, provides the elegant solution to the edge wrapping hazard. This matrix illustrates the mask. It indicates which pixels physically belong next to each other, populating the false wrapped connections with negative infinity. Applying negative infinity forces the softmax output to exactly 0, severing cross-boundary connections while maintaining parallel processing for valid pixels. Steps 4 through 6 proceed normally on this safely masked data. In Step 7, Reverse Shift, and Step 8, Window Merge, the tensor is unrolled back down and to the right, returning it to its true spatial alignment. Cyclic shifting paired with masking enables complex cross-window communication without expanding the tensor size or relying on slow, custom CUDA loops. Stacking WMSA and SWMSA blocks sequentially throughout the network layers generates a compounding effect on spatial awareness. Watch this fluid visualization closely. Shifting the window boundaries back and forth continually creates these expanding, overlapping regions of information transfer. A pixel's receptive field begins strictly locally, but as it passes through deeper layers, that field organically expands to encompass the entire high-resolution image. This alternating architecture ultimately achieves the macro-level understanding of global attention while strictly enforcing the micro-level computational constraints of local attention. The hardware impact is definitive. This tensor pipeline entirely eliminates the O of n squared memory explosion. By treating spatial patches as massive batches, the sequence length, the true computational bottleneck of transformers, is permanently locked to m squared. Eliminating the quadratic growth of the attention matrix allows transformers to handle dense prediction tasks, like image segmentation and object detection, at high resolutions. The Swin architecture prioritizes the organization of memory and the careful reshaping of tensor dimensions to bypass the physical limits of current hardware. Understanding modern AI architecture requires looking past the simple conceptual diagrams and mapping the data dimension by dimension.